Hello everyone. First of all, I would like to thanks for this great opportunity to share my work with you. Today, I would like to talk about the current limitations of using facial photo to diagnose the rare disorders, and how we utilize our Gestalt Match approach to tackle the limitations. With the recent advances in computer vision and machine learning, the next generation phenotyping technique has become very popular for syndromology. It enables us to learn the facial representation of the disease by training on patient's photo, and further help us to diagnose the patient. For example, here we first train the deep convolutional neural network by the patient's photos to learn the facial dysmorphic features. And further, by analyzing the photo of this patient, we can measure the similarity to the syndromes we trained in the network. And the most similar syndromes here is Cohen-Cyrus 1. So we could further check the mutations related to Cohen-Cyrus 1 and diagnose this patient. The NGP technology has significantly progressed in the last few years. From 2014 to 2019, the training scale has increased from 8 syndromes in Ferry paper to over 216 syndromes in Gurovich paper, which is behind Face2Gene platform. The method described in this paper is also called DeepGestalt. And I will use this term to refer to this study in my following presentation. Moreover, beyond the syndrome classification, the study from Donk used the method from Ferry paper to identify the distinguishable faces on 3 novel disease genes. And later in 2019, the study from Marbach found a new disease caused by LEMD2 gene by matching patients with the similarity score from DeepGestalt method. Therefore, we started to move from the classifying known disorder to discovering novel disease. However, before we dive into the technology, I would like to invite all of you to guess the differential diagnoses that come to your mind for these 3 patients. If we ask the same question to DeepGestalt, which is Face2Gene, we will get the following suggestion. Kabuki and HPMS are correctly listed on the first rank. For the last patient, I placed the card of the correct diagnosis on the top, because this novel disease is not supported yet in Face2Gene. I assume that many of you were right about the first diagnosis. Some of you probably also got the second one, but maybe only very few of you know the disease-causing gene in the last patient. You might wonder why. Here I visualize how many pathogenic submissions we can currently find for the respective disease genes in ClinVar, and this also correlates roughly with their prevalence. Therefore, the most likely explanation is that physicians are better at recognizing dysmorphic syndromes that are more frequent. Similarly, the artificial intelligence that needs to learn the syndromes from the patient's photo will also have the same problem. If we have too few photos or we don't have photos, then of course we are not able to learn the facial representation of the disease. And the current limitations for DeepGestalt to learn a disorder is around 7 patients. Therefore, here we propose the GestaltMatch approach as extension of the Gestalt approach. First of all, we aim to support more ultra-rare syndromes and push our limit to the long tail on the right. And secondly, we want to increase the scalability. For example, if our model is originally trained on these 4 syndromes, but today we want to add another novel disease into this model, then we need to retrain our model, which might require lots of time and also lots of money. So we want to be able to include the new syndromes without retraining the model to be more flexible. In the end, clinicians are always looking for similar patients. Therefore, we want to also be able to quantify the similarity among the patients, which can help the clinician to find a similar patient, and also explain the relationship between patients and the disorders. Now I would like to introduce how we extend DeepGestalt to GestaltMatch approach. First of all, the deep convolutional neural network in DeepGestalt can be divided into feature encoder and classifier. Feature encoder is to learn the facial features, and classifier is to classify the disease we trained in the network. The network is trained on 21,000 images of 301 syndromes. We took the last fully connected layer in the feature encoder as facial descriptor, and we further span the clinical face phenotype space by this 320-dimensional facial descriptor. Each patient is a point located in this space. We can further do the classification on all the 1,400 syndromes we have in this space, and we no longer restrict to the 301 syndromes we trained in the model. In the phenotype space, the similarity between two patients is quantified by the cosine distance between two patients in the space, by projecting the patients into two-dimensional space on the left. And here we can see that if the patients are close in the space, they do have similar phenotype. And then, how do we evaluate the performance? This is the patient with coven serous. By putting these patients into the phenotype space, if the nearest patient in the space also has coven serous, then we call it top 1 match. Moreover, we have a patient with Noonan syndrome. If another patient with Noonan syndrome is in the 5th position or better than 5th position, then we call it top 5 match. It also applies to top 10 or top 30 match. Now I want to show you the performance of Gestalt Match, and also the reason why we don't simply use the normal face recognition instead. First of all, the training data we use include the 500,000 healthy photo from CASIA web face to initiate the general features, and it is just like the normal face recognition. And we later fine-tune on 21,000 patients' photo for dysmorphic features. So here we compare the performance between training the model with patient and without the patients. In this evaluation, we test 1,700 images in the space with 34,000 images over 1,400 syndromes. In this figure, the x-axis is the top 1 to top 30 rank, and y-axis is the accuracy. And we found that the model of including patients clearly outperformed the one without the patients. The top 10 accuracy increased from 51% to 66%. Therefore, it is crucial that we fine-tune our model on patients' photos. Moreover, we wonder whether we can classify the novel disease we haven't seen in the model yet. The previous approach, like DeepGestalt, is classifying the syndromes we trained in the model. GestaltMatch aims to learn the facial features from the syndromes we trained in the model to match the patients with syndromes which are not present in the model. Just like the star and the cross here, they are not present in the training set. In order to prove we can classify novel disease, here we select 40 syndromes and train two models. One is including these 40 syndromes, and another one without these 40 syndromes, and further test on these syndromes. This figure is the performance comparison between including these 40 syndromes in the training and not including them in the training. From the results, we found that there is no significant difference between whether the syndromes are included in the training or not. Therefore, we know that GestaltMatch can discriminate the novel disease we haven't seen before. In the end, we wonder whether prevalence influences the distinguishability. Is the syndromes with higher prevalence easier to recognize? In order to investigate the correlations between prevalence and distinguishability, we select 40 syndromes, and for each syndrome, we randomly downsample to 10 patients to make sure all the syndromes have equal number of patients to remove the confounding effect from the prevalence. We do this experiment 1,000 times. This figure shows the results of averaging 1,000 times of this evaluation. The x-axis shows the syndrome prevalence by the ARPANET, and the y-axis is the average top 10 accuracy, starting here at 40%. Each point here is a syndrome. We can see that the accuracy y doesn't correlate with the prevalence x. Lots of syndromes with low prevalence still perform very well. We can further consider the accuracy as the distinguishability of the syndrome. Therefore, as distinguishability doesn't depend on the prevalence, the ultra-rare disorder with a high distinguishability in the upper left corner will be the low-hanging fruits for Gestalt Match approach. Since we can measure the similarity among the patients and match patients with the same syndromes, so we can also consider Gestalt Match as the facial image versions of GestaltMatcher. Once the similar patients are found, the clinician of two patients can contact to each other and discuss the similar mutation. Therefore, if you have unsolved patients and would like to join us, please simply check the box of patient matching in your patients page in Face2Gene platform. Once we have the matched patient, you will receive our notification. From the results, we can see that our Gestalt Match approach can classify the novel ultra-rare disorders, which enable us to explore rare disorders faster. Moreover, it took us 5 years to move from 8 syndromes to 200 syndromes. With Gestalt Match approach, we might not need another 5 years to get into the next level. And if you are interested in our study, you could also find our study in bioRxiv preprint server. In the end, I would like to thank to our colleagues in IGSB and all the collaborators from FDNA and Charité Berlin, and also the patients and their family. And thank you. I'm happy to answer all the questions.